In this video, I'm going to talk about a couple of advanced GD&T topics that you need to know for the certification exam and for design in general. So the topics are inner and outer boundaries and virtual and resultant condition, and specifically how to figure out what they are on a given feature on a given drawing. So I'm going to go through the definitions. I'll be reading them to you, but I'll also put it on the screen so you can read it for yourself. This all comes from section 1.3 of the 2009 ASME standard. So let me get through reading these and then I'll explain what everything means. 1.3.2, boundary inner. A worst case boundary generated by the smallest feature, so MMC for an internal feature or LMC for an external feature, minus the stated geometric tolerance and any additional geometric tolerance, if applicable, resulting from the feature's departure from its specified material condition. 1.35, boundary outer. A worst case boundary generated by the largest feature, LMC for an internal feature, MMC for an external feature, plus the stated geometric tolerance, if applicable, resulting from the feature's departure from its specified material condition. 1.3.51, resultant condition. The single worst case boundary generated by the collective effects of a feature of sizes specified MMC or LMC, the geometric tolerance for that material condition, the size tolerance, and the additional geometric tolerance derived from the feature's departure from its specified material condition. 1.3.67, virtual condition. A constant boundary generated by the collective effects of a considered feature of sizes specified MMC or LMC and the geometric tolerance for that material condition. So if you're still with me, let me try to explain what some of these mean. What you're really looking for, and the way I like to phrase it, is how much room can a feature take up. So let me give you an example. So on the board, all I have is a hole going through a block. So no tolerances, no geometric tolerances or anything, but we just imagine, that this hole should be straight, but it's not. Whenever you apply a position tolerance, you're implying that there is tolerance. The hole doesn't have to be perfectly straight. The size tolerance also adds to this because now the hole can be larger or smaller. So in this case, without knowing any tolerances or anything, we could say our inner boundary, so the smallest thing that could fit in here and be perpendicular to one of these faces, is right here, right? So from this point to this point, this would be the smallest diameter that could fit through there. Now, a position tolerance is going to be related to something. When we're thinking about how parts fit together, this matters. The outer boundary is going to be the most room the feature can take up. So we want to consider this when we're thinking about wall thickness, right? So it's not going to be readily apparent, and I'll give you an example later, how much wall thickness you're going to have just by looking at the size tolerance and the position tolerance. So this maximum room it can take up is dependent on both the size and the geometric tolerance. So let me go through the list of all of the boundaries. So this is how I do it. We've got inner and outer boundaries for plus or minus features, features modified at RFS, features modified at MMC, features modified at LMC. Now for each, we've got internal and external, and they will each have their own inner and outer boundaries. So we have a lot to fill in here, and I'll go through how to figure out what they should be. This isn't something you really have to memorize this whole chart. It should come pretty naturally when you figure out what the inner and outer boundaries are supposed to be. And then resultant condition and virtual condition are just variations of inner and outer boundaries. They only apply with MMC or LMC. Now first, let's look at plus minus dimensions. So we've got drawn up here an external feature, a pen, an internal feature, a hole, no geometric tolerance, just plus or minus dimensions. The outer boundary of the pen is going to be its MMC, the largest it can be, right? So it's kind of telling you how much room the pen can take up or how large the mating hole would need to be to have the pen fit freely. So, outer boundary is 1.02. Inner boundary of the pen is going to be its LMC, so the smallest it can be, 0.98. For the hole, we're going to reverse it. It's going to be opposite. The MMC of the hole is the smallest the hole can be. So in this case, 0.98. The outer boundary of a hole is the largest it can be, in this case, 1.02. So if we compare the outer boundary of the pen to the inner boundary of the hole, we can see they're not going to fit together, right? Because the nominal is the same and they both have the same tolerance applied. We'd have to change this dimension to make them fit. Now, to write it up here, our inner boundary for an internal feature is the MMC. The outer boundary for an internal feature is the LMC. It's opposite for external. The inner boundary is going to be the LMC. The outer boundary is going to be the MMC. So see what I mean? You don't really have to memorize this. If you just think about the objects, it should come pretty naturally. Now, for features modified RFS, so that's when you don't have a MMC or a LMC symbol and something that's a feature of size. So in this case, I'm just going to use a straightness applied to a derived median line just because it's the quickest to show, but this would work for position or perpendicularity, other tolerances as well. So we've got a straightness tolerance applied to the derived median line because it's a feature of size and it's adjacent to the size dimension. This is going to change our calculation of the inner and outer boundaries because the straightness tolerance allows you to break rule number 1. Essentially, if this pen is at MMC, so 1.02, and you have 20 thousandths of tolerance on that derived median line, it allows the pen to be bent. So if the pen comes in at 1.02 and it's bent 20 thousandths, it's going to take up a larger space. You would need a hole that's 1.04 to fit that pen. Okay, so we're going to reflect that in our calculations right here. So I changed the order here to reflect the order I have over here. Hopefully it makes it a little easier. So the outer boundary of the pen is going to be the MMC plus the geometric tolerance, okay? So we're gonna 1.02 plus 20 thousandths, in this case, 1.04. The inner boundary is the LMC minus the geometric tolerance. So in this case, 0.98 minus 0.02, 0.96. So if we write it over here for our external feature, the equation would be, for our external feature, it's MMC plus the geometric tolerance. The inner boundary is LMC minus the geometric tolerance for an external feature. For our internal feature, our outer boundary is going to be the LMC, but it's still the largest size, okay? So it kind of flip-flops. So 1.02 plus 20 thousandths is going to be 1.04. And our inner boundary is 0.96. So if we write it in our chart over here, the outer boundary is the LMC plus the geometric tolerance. The inner boundary is the MMC minus the geometric tolerance. Now, if you think back to the definitions I gave you before, I'll just read real quick. Inner boundary, a worst case boundary generated by the smallest feature, MMC for an internal feature, or LMC for an external feature, minus the stated geometric tolerance. We haven't gotten to the point of any additional applicable tolerance. That's going to be bonus tolerance generated by MMC or LMC, but you don't have to worry about that if it's at RFS. Again, according to rule number 2, we don't put this S symbol in the feature control frame. It's a default requirement. Okay, I just put the S symbol here because it used to be the symbol for RFS. Now, we're all good here. We've got to move into calculating inner and outer boundaries for MMC, and this is where we're going to start to run into virtual condition and resultant condition. So I'm going to add the MMC symbol over here. It's going to change our calculation a little bit, so let's think about it. We've got an external feature, 20 thousandths tolerance, but only at MMC. If the feature comes in at a size less than its MMC, you get more tolerance equal to that difference. So we're only caring here about worst case scenarios, right? Not the actual size the part came in at. So for all of these, the additional tolerance, the bonus tolerance, is going to be equal to the total size tolerance. In this case, our total size tolerance is going to be 40 thousandths. So plus or minus 20 thousandths is 40 thousandths. That is the most additional tolerance we can get, and it's what we care about for these calculations. So our outer boundary is the MMC of the pen plus the geometric tolerance, and that's it. But the inner boundary is going to change, right? Because we get more tolerance as the feature departs from MMC. That more tolerance is 40 thousandths, like I mentioned before, plus this 20 thousandths. So we're going to have 0.98 minus 60 thousandths. That's going to give us 0.92. That is the effect of the MMC on the inner boundary of this feature. Now, let me write it over here for you. So the outer boundary is the MMC plus the geometric tolerance. The inner boundary is the LMC minus the geometric tolerance minus the total size tolerance. I've abbreviated it TST. So let's go to the internal feature here. Again, it's going to flip. So this hole is 20 thousandths at MMC, so the smallest hole. So our inner boundary is going to be 0.98 minus 20 thousandths, 0.96. And our outer boundary is going to be 1.02 plus 20 thousandths plus 40 thousandths. So the outer boundary can grow, and that's what the MMC does. It allows the hole to get larger and still pass an inspection for things like clearance holes. So written over here in equation form, our inner boundary, the inner boundary of the hole is the MMC minus the geometric tolerance. The outer boundary is the LMC plus the geometric tolerance plus the total size tolerance. Okay. Now, this is a time to bring up virtual condition and resultant condition. So the virtual condition for an external feature is the outer boundary. So you could call this the outer boundary or the virtual condition. It means the same thing. So back to the definition, a virtual condition is a constant boundary generated by the collective effects of a considered feature of sizes specified at MMC or LMC and the geometric tolerance. That's it. There's no bonus tolerance applied to it. So just by looking at this, we can tell it's the virtual condition. It has to be either MMC or LMC to be a virtual condition. I'm out of room to write, so I'm just going to circle those. That's the virtual condition. The resultant condition is just the opposite. So this is a virtual condition. This is the resultant condition. The resultant condition is going to take into account the total size tolerance. So there's an extra step there. Now, normally this is where you could stop in a typical designing because LMC doesn't get used that often, but I'll go through it anyway. LMC is just going to reverse all of the MMC stuff. So if you're learning this for the first time, you might just want to focus on these first few and skip LMC because it can get confusing because you're reversing things. So So let's jump into features modified at LMC. So if this tolerance only applies at LMC, it means as this pin gets larger within its size tolerance, you get more tolerance. Okay? So the inner boundary of this pin is protected by the LMC. So the inner boundary is 0.98 minus that 20 thousandths. The outer boundary of the pen is allowed to grow because now you can use the bonus tolerance you get with LMC. So in this case, we're going to take in, for our outer boundary, our MMC plus the geometric tolerance plus the total size tolerance. So 1.02 plus 40 thousandths plus 20 thousandths is going to give us 1.08. And I'll write this down here. So for a feature modified at LMC, the inner boundary is the LMC minus the geometric tolerance. The outer boundary is the MMC plus geometric tolerance plus total size tolerance, as opposed to modified at MMC where it's reversed. Okay, so you're just reversing these. Now, for an internal feature, we're protecting the outer boundary. So 1.02 plus 20 thousandths gives us 1.04. Our inner boundary can shrink more. So 0.98 minus 20 thousandths minus 40 thousandths. Our inner boundary is going to be 0.92. So the hole is allowed to shrink more as opposed to MMC where it's allowed to grow larger. So down here for a internal feature modified at LMC, our internal boundary is going to be our MMC minus the geometric tolerance minus the total size tolerance, and the outer boundary is our LMC plus the geometric tolerance. So we're essentially not allowing the hole to grow too much. So you use this in situations where you have like thin wall conservation in mind. Again, with LMC, whenever you're not taking into account the total size tolerance, that's your virtual condition. So I'll go ahead and circle these. So for a LMC external feature, the inner boundary is the virtual condition. The outer boundary is the resultant condition because you're taking into account the bonus tolerance or the total size tolerance in this case. So I'm going to erase all my beautiful handiwork here and go through an example of a thin wall calculation to kind of show you where you use inner and outer boundaries. Okay, so I got an example on the board, just a thin-walled washer. The outer diameter, we're going to consider a datum feature. One of the flats, so the whole side of it, we'll consider datum A. So what we can do here is compare the inner boundary of this feature to the outer boundary of this feature and see if there's wall thickness there. See if we have a zero wall thickness problem. So you can't do this with just the size dimension, right? Just size dimension, this checks out. So the outer boundary of this would clear the inner boundary of this. We've got to take into account the geometric tolerance. So let's break it down this way. The inner and outer boundaries of a plus or minus feature are just the MMC or LMC. For this feature, we're going to use these two equations from the chart that I had up here a second ago. So the outer boundary, LMC plus geometric tolerance plus total size tolerance, inner boundary, MMC minus geometric tolerance. We don't really care what the inner boundary is, we only need the outer boundary for this calculation. So I'll write it up here. Outer boundary, our LMC, is 2.91. So the largest size of the hole. Geometric tolerance is 0.04, and our total size tolerance is 0.04. So our outer boundary is 2.99. Inner boundary here is 2.98. This part would fail a minimum wall check, right? There's a worst case scenario where the outer boundary of the hole is larger than the inner boundary of the outside. The reason is because well, aside from just generally applying dimensions and tolerances, the reason is that we use the MMC modifier, right? It's very common to apply MMC to basically everything. It gives you more tolerance, but there are certain cases where it's not a good idea. So let's take a look if we didn't use the MMC modifier. What if we get rid of that? That's going to change our calculation. The outer boundary is now just going to be the LMC plus the geometric tolerance at RFS, inner boundary MMC minus geometric tolerance. Now we do have enough wall thickness, even at worst case with RFS. We could take it a step further and use LMC. But what the LMC is going to do here, it's not going to give you more tolerance for the outer boundary of this hole. It just makes it easier to manufacture because now the inner boundary can be smaller. Okay, so it just gives manufacturing more wiggle room when they're trying to drill. They can drill the hole smaller and then make it a little bit bigger as they go. So LMC is often used for this kind of thing, but you still have to do the calculation to figure out whether your inner and outer boundaries match. Now, inner and outer boundary calculations can be used for a whole lot of things, and tolerance calculation like this. They can't be used for everything. Sometimes you need the vector method, but the boundary method is great for just quick calculations like this to see if two parts will in fact fit together at worst case conditions. So that's it for this video. I hope you got something out of it. This kind of stuff comes up on the ASME certification exam all the time. You got to know virtual condition, resultant condition, inner and outer boundaries. But it's good to know that they're all connected, okay? So if you enjoyed the video, please like and subscribe, leave a comment down below.